So in part B of our chemical bonding series, we're going to look at metallic bonding. So metallic bonding is the bonding that exists between metal atoms in a metal. And the best way to think about this is it's a lattice of metal cations surrounded by a sea of delocalized valence electrons. So let me try and explain to you a little bit more what that means. We will take our example as lithium, just because it's in a sense the simplest metal, atomic number 3. It has an electron configuration of 2, 1, so it has 2 electrons in the first shell and then 1 valence electron in its outer shell. And remember what I said in the last video, everything wants to have a full or an empty outer shell, and in the case of metals that's usually an empty outer shell. So how is this achieved and how does this relate to metallic bonding? We can think of each of the lithium atoms forming this lattice of lithium atoms with their 2 core electrons closely attached. So those core electrons stay attached to each lithium atom. There's obviously only 2 core electrons, there's 3 protons in the middle of lithium, so we can think of this like being a lattice of lithium ions surrounded just by their core electrons. Those valence outer electrons basically are what we call delocalized, and that's a fancy way of saying they don't stay attached to any individual lithium atom. They're actually free to move through the lattice, through the structure of the metal. And we'll see in a sec how that relates to some of the properties of a metal. So that's, if you like, this picture that we need to have in mind when we think about how the metal atoms bond together in a metal. So how does that relate to their properties? Well, metals tend to have high melting points, and that's because of the strong electrostatic attraction between the positively charged metal cations, each of our lithiums here, and the negatively charged electrons between them, which act, if you like a glue, all oppositely charged, holding everything together. Metals can also conduct electricity really well because these electrons are free to move through the structure, and electricity is basically a flow of charged particles. Electrons are charged particles, so if we can have the movement of charged particles through a substance, then it can conduct electricity. So that's how the delocalized electrons achieve that. And finally, metals tend to be malleable and ductile, so they can be pressed into shape and drawn into wire and that sort of thing. And that's because basically these electrons, because they are free to move, they act like a flexible glue. So they don't sort of lock the structure together really tightly. As you bend the metal, as you press it, they're able to basically move themselves. And as they move themselves, that basically provides that flexibility within the substance. I haven't talked about this here as well, but I know it does come up in the book. Metals also tend to be good conductors of heat because as you heat a metal up, all of the particles will vibrate faster and faster, and then in particular these free delocalized electrons will vibrate faster and faster, and then as they move through the structure, they will basically keep those vibrations going through the structure, make all the particles further down the metal vibrate faster and faster, thereby allowing it to conduct heat. It doesn't specifically mention that in the subject outline, but it is covered in the book, and I think it's an important property. So there you have it, the metallic bonding model. Most people find this one fairly simple to understand. Hopefully I've explained that in a way that makes it fairly simple for you. Thank you.